Welcome to The Explainer. Today, we're going to talk about something that is literally all around you, something that shapes the very ground we walk on and manages our most precious resource, water. We are talking about watersheds. So let's start with a really simple question. You see it rain, the water hits the ground, and then what happens? Where does it all actually go? The answer to that question is really the key to understanding everything we're about to get into. Okay, so what is a watershed? Well, the textbook definition says it's an area of land that channels all the water to a common outlet, like a river or a lake. But let's put it another way. Just think of it like a giant natural funnel for collecting water. Now, that definition might still feel a little abstract. So let's use a great analogy to really make this click. I want you to picture an umbrella, but flip it upside down, like you were trying to catch the rain. This is a perfect visual for how it works. The fabric of that umbrella, that's the land area of the watershed. The rim of the umbrella is the boundary. And any single raindrop that falls inside is guided all the way down to that one central point at the bottom. And that, in a nutshell, is a watershed. But here's the thing, a watershed isn't just a simple bowl. Oh no, it's a super complex, interconnected network. You can almost think of it like a family tree for rivers. So let's break down how that whole network is organized. With all these streams and rivers flowing into each other, how in the world do scientists keep track of them all? Well, they use this really clever classification system. It's called stream orders, and it's basically a way to give every single channel a rank within the whole system. Everything has to start somewhere, right? For a watershed, it all begins with the absolute smallest trickles of water, those tiny, unbranching channels way up at the top. These are called first-order streams. They are the headwaters, the very source of everything that flows downstream. The way the system builds is actually kind of beautiful. It follows one simple rule. When two streams of the same order meet, they form a stream of the next order up. So two first orders come together to make a second order. Two second orders merge to create a third order. You get the idea. It's this clean, logical progression from the smallest streams to the mightiest rivers. And what's really amazing is that this system actually reveals a pattern in the landscape itself. Those little first-order streams, you usually find them in steep, mountainous areas, carving out sharp, V-shaped valleys as they rush downhill. But as they merge and become these bigger, higher-order rivers, the whole landscape changes. The slopes get gentler, the valleys open up and get broad, and the rivers start to do that classic lazy meandering thing across the land. Okay, so we're starting to get the network inside the watershed. But what about the edge? How do we actually draw that line around it? The rim of our upside-down umbrella. Well, that process is called delineation, and it's all about finding the boundaries. The most crucial point to remember here is that topography is everything. Water always flows downhill, which means the boundary of any watershed, that line that separates it from its neighbor, is always going to be the line of highest elevation. We're talking about the ridges and peaks that literally divide the flow of water. Now, that makes perfect sense if you're standing on top of a mountain, but how do you see those high points on a flat piece of paper? How can you trace a watershed boundary just by looking at a map? The tool for the job is a topographic map. Topographic maps show elevation using these things called contour lines. Now, for our purposes, there's a simple little trick to reading them. When the V shape of the contour lines points uphill, you're looking at a valley or stream. But when that V shape points downhill, that's it. That's a ridge. That's the boundary we're trying to find. So with that little trick in your back pocket, the whole process breaks down into two main steps. First, you just identify your outlet. That's the point on the stream that you care about. Then, starting from there, you draw a line that connects the highest points of elevation all around it, always trying to cross those contour lines at a right angle. And that line you just drew, that's your watershed boundary. Okay, so we've defined a watershed, we've organized its streams, we've even drawn its boundaries on a map. But why does any of this matter in the real world? This is where we get to the practical stuff. You see, knowing the exact size and shape of a watershed lets engineers calculate really critical variables. And one of the most important is what's called the time of concentration. It is exactly what it sounds like, the time it takes for a drop of rain falling on the most remote part of the watershed to travel all the way to the outlet. This tells you how fast a watershed responds to rain. And that single number is unbelievably powerful. It helps city planners design storm drains that can handle a downpour. It allows forecasters to predict how quickly a river might flood. It even helps scientists track how a pollutant might spread through a system. And think about this. What happens when we pave over all that land with concrete? The water can't soak in, so it runs off way faster, which dramatically shortens that time of concentration. This is a huge reason why urban areas are so prone to flash floods. So, from just a single raindrop to a complex map, a watershed isn't just some feature on the land. It's a dynamic system that tells a story. It affects everything from flood control to the quality of our drinking water. Which leaves us with one final thought. Every single watershed tells a story about the land it covers. Do you know yours?